you is we will close with the experience from Norway, NGI.
Yes, thank you. So yes, I guess I am the final presentation. So
You are.
what's separating you from the bar? So I'll try to keep this relatively swift. There's a lot of pictures, less technical than the other presentations. I guess that's kind of a reflection of industry over university, perhaps. Anyway, so this presentation is kind of NGI's perspective of some challenges we're facing in terms of the amount of data and where our data is coming from and how we're using that data. So I'm going to be presenting sort of like, you know, the in-sources of data that we're receiving and what we're doing with them and what solutions we're providing to the industry. And then I'll follow that up with an example project where we've had sort of a huge amount of data to deal with and to deliver products. And that's for one of the Dutch wind farms that Hawk has already mentioned in terms of this sort of freely available data set, which NGI has been part of. So here at NGI, we have a whole department named Geodata and Technology. So basically, the whole goal of our sort of market area is can we combine our knowledge of soil and our growing knowledge of data and data management, and then look to the future to create better solutions. So NGI, as I guess you all have sort of know about the history of the company, but it's sort of based upon three pillars of sort of characterization, modeling, and validation. This is particularly key in the offshore energy sector. And feeding into all these three different categories is a whole load of data. We get data from historical records, not necessarily digitized, but perhaps need to be sort of hand digitized or put into some sort of database. We get a lot of data now from site investigation. When we're talking about offshore wind farms, we have hundreds of kilometers squared area of geophysical data coupled with hundreds of CPTs sort of peppered across the site. And this is all, you know, combined with tens to maybe hundreds of borehole locations too. So we have to manage this data as best as possible. We also do quite a lot of physical modeling, both on land. So at the top left, you'll see our site, one of our sites, the Norwegian geotechnical testing sites. I think we'll be presenting a bit more about that later in the GeoLabs sessions. Then we also do testing offshore, and this is from a recent Taiwan pile testing program. And the data collected here is used directly into enhancing design methods. To the right, we have monitoring. So of course, we have a whole monitoring section, and we have fiber optic strain gauge sensors placed upon this monopile, which has gone directly into the field. We also collect data from structural health monitoring. Here you'll see a tripod jacket on buckets, on suction buckets, fully monitored with strain gauges, accelerometers, pore water pressure sensors, and we get a whole host of data coming out of that, which is very valuable for both ourselves and also the industry in progressing, and I guess yourselves in academic side, where we progress our technical models. And we can use this data to check, for example, the natural frequency response of the system, as well as looking into accelerations and displacements, and how this evolves with time. So what do we do with this data? So obviously a growing phenomenon within the engineering atmosphere would be digital twin modeling. I guess it's quite juvenile in geotechnics, but we can use this data to calibrate our models and then perhaps predict how the asset will perform into the future. We're quite involved now with a lot of live data streaming. So we have installation jobs where we are putting the data over the internet to our clients who don't necessarily have to come to the vessel anymore. And we can have conversations from their office to the vessel, and without the need to have, it's quite very expensive to take the client on board. So it's a very attractive option for them. And finally, of course, back analysis, very historically important use of the data. But here we have an example where we have GBS Foundation done by physical modelling, back analysed against a computed FE study. We're also building large geotechnical databases and enhancing empirical frameworks that we use every day in our design practice. And by collecting data from more relevant sites for offshore wind, we can then apply them into future offshore wind projects with more confidence. Here you'll see a collection of very well-known databases that with every project we do, we add more and more data to those. And it is, of course, NGI's sort of philosophy to try to share as much of that data with the public as the client will allow. And then finally, once we've collected the data and managed the data and stored the data and everything, what is the final application of that data? You'll see on the top left, we are creating integrated ground models of whole wind farm developments. This is what I'll be talking about in the second half of the presentation. We are looking at design improvements. So I guess you'll all notice the PISA project spring modifications, but that was obviously developed using data collected from physical model testing. And then looking to the future, we can use the data from our digital twin aspects into looking at lifetime extension. So I guess all that sort of very short blurb of data is sort of, we're here at NGI, we're very interested in data. So, we're trying to collect it and understand it as best as possible. So this particular project I'll present very briefly is an example at NGI where we've had sort of a big collection of data and provided a product based upon that data. So this is from the TNW offshore wind farm off the coast of the Netherlands. It is incidentally as Hogg mentioned, it's all funded by the Dutch government. So all the data and all these adjoining reports that I will present are freely available to anybody using the link provided, which is really good. It's a new initiative to try to allow contractors and developers to maximize their designs and installation processes without having to do the site investigation themselves. So it sort of bypasses that first contractual step. So the TNW wind farm is a rather large area. So we're looking at 120 kilometers squared. So approximately the same size as Amsterdam. So if we wanted to do a full ground model of Amsterdam, it would be quite challenging. So we're looking at the same sort of variability in geotechnical parameters across that site, but we have to provide an integrated ground model that captures all that complexity. So I guess historically, we may have had CPT and borehole, or a selection of borehole investigations at each individual wind turbine. But now, as budget becomes more constricted and time is very tight, we may have only a collection of CPTs across the whole site, and we have to sort of interpolate in between using more ingenuitive methods. So this is where we can create this integrated ground model that sort of combines the geological, the geophysical, and the geotechnical data together. So individual contractors have gone out across the TNW wind farm and collected the data. This being, as I said, the geological, geophysical, and geotechnical. These are then integrated within NGI and partners across the project to create a geological ground model. So this is geologically correct. It's not a case of we are at each individual wind turbine location and sort of just interpreting that location individually. We're having a spatially correct and accurate and understandable model. And then from there, we can do CPT predictions from within the locations where we haven't tested. The final outcome is, of course, the development of this integrated ground model. And what we do is we have sort of an iterative process whereby we create one level of integrated ground model based upon the first site investigation. We then analyze where we're lacking data or perhaps have a bit more uncertainty, and then we can go out back into the field and collect more additional measurements. This is very useful for the contractor because it obviously allows them to save time perhaps on not investigating where it's not necessarily needed. And then finally, obviously the overall goal is to create geotechnical design profiles at the wind turbine generator locations. So yes, I'll very briefly show some pictures, some nice pictures, and just sort of guide through how this process was evolved. So yes, the geology, it's not my specialty, but I guess they have historical geological maps that they've scrutinized, as well as combining with the geophysical data, managed to create a 3D representation of the geology of the TNW site. So we have geological horizons that are sort of present across most of the North Sea. But yes, so this kind of forms the basis for piecing together the other less spatially represented data we collect. So this is obviously a 3D data. And then when we come to the geophysical aspect, it's a series of 2D measurements along a number of slices across the site. So here you can identify your soil unit boundaries and any changes in lithology, that sort of thing. But again, it's not in a 3D model, so we have to sort of create a representation of these 2D slices across the whole site. And then when we come to the geotechnical measurements, these are now 1D measurements with depth. So as I said before, historically, we may have relied upon these 1D measurements at each individual location and taken those forward into design, but perhaps the wind turbine generator layout changes with time and we want to change the locations. It's not necessarily possible to go out and do another CPT or another borehole at that location. So we have to then think creatively and sort of interpolate those CPT responses at new locations. So we have across the TNW site, we have CPT measurements, borehole measurements, borehole collected samples which go into the lab, as well as the vibrocore samples. And these are all sort of collected to create a database of soil. Okay, so that kind of covers where the data is collected, and then we need to do something with that data. So we're talking hundreds of gigabytes of data that we need to manage and create into a product for basically the Dutch government who are looking for this integrated ground model. So the first step from that is to build this 3D structural ground model, which combines the knowledge we learn from the geological sort of 3D model, the 2D geophysical horizons, and those 1D geotechnical sort of strength parameters. So we can create this 3D, the eventual goal is to create this 3D soil unit model, which has strength parameters associated on every, 3D point in space. So obviously coupled with that is a level of uncertainty, which we then have to obviously take forward into design. If the uncertainty is too large at a particular point where you want to perhaps eventually place your wind turbine, then maybe it's wise to go out and do a particular investigation at that location. But if the uncertainty is very low, it doesn't necessarily warrant the need to go out to that particular location. So it allows the developer to have a better control of their uncertainty within the model, the 3D space that they are dealing with. So what we can do from this 3D geological ground model is to sort of scrutinize any point across the site, and it will give us a predictive model for a CPT and its CPT parameters. So obviously the QC, FS, and U2 sort of directly measured parameters. And what we can do with this is have a number of locations where we have measured with CPT data and train the sort of the inversion from this 3D data set to match the measured CPT locations, and then sort of with time and iteration reduce the uncertainty at those trained locations and try to map that across the whole site. So you'll see, obviously I have just picked out a random point on the map, but actually I think that's where we have a CPT, and then we have this level of probability, or I guess uncertainty, or the opposite of uncertainty, where we are showing that, at depth, of course, we have very high probability that the CPT is correct, but at higher levels, maybe we need to refine that model and then we reiterate again. So what we can do to help us with that process is to combine the geophysical measurements with the geotechnical measurements. So at an individual geotechnical CPT measurement point, we can compare the shear impedance and the shear attenuation of the geophysical measurement with depth with the CPT geotechnical strength measurements. So that will basically be an iterative training of the data set. So we're basically training our large model to perform as we want it to perform across the whole site. This slide just sort of shows the different stages that we go through in terms of training the model. So we have sort of prediction errors, which we scrutinize, and we want to obviously narrow those bands of prediction errors. And we're also looking at sort of when we do have our measured and predicted CPT at the same location, what is the cross correlation between those two values? Obviously, we have a one-to-one relationship. If the values are close to that one-to-one, we have a better model. If not, then we need to reevaluate our model translation. So I guess the goal then is to have a model that is able to predict the CPTs that are measured, and then therefore give us confidence that where we haven't measured, we have a good CPT. So this particular slide is just showing that in the background of those sort of seismic horizons, which have been translated into geotechnical parameters, is the QC, the FS, and the U2 predicted from the 3D space. And on top of that, which is difficult to see, but that's because they're well trained, is the actual measured values of that. So you can see, especially with the QC on the left, that the response is very strong. So it gives us confidence that when we go into scrutinize a location where we don't have any information, we can create a CPT profile and then take that into design profiles forward. So I guess one thing to note is, of course, there is a level of uncertainty involved with this. And we create, for example, a best estimate prediction of the CPT response, but then we have to add on confidence levels based upon various levels of various aspects within this inversion process from the three data sources. It's not necessarily my area of expertise, but I can try to explain as best possible. So we have an original sort of best estimate, let's say the C line, which is maybe used in the final design. Then we have two associated B and D with a confidence level of 95%. 1 minute, I'm nearly finished. We add a level of uncertainty for the 3D interpolation. And then, of course, we have uncertainty in the structural model in terms of the boundary locations, which we need to incorporate. All these are taken forward and into the final sort of design profiles where we may have lower best estimates or lower estimates, for example, for our final design. So finally, of course, so the deliverables of this collection of data that was sort of dumped in let's say a Dropbox file by the client, we then provide a full 3D space structural model and a full 3D space predicted CPT parameter model. What we can do then, of course, is pull out at any given location the soil unit layering, the CPT parameters, and the derived parameters. This is then taken forward into the geotechnical design. So this whole holistic approach has been adopted by the Dutch government to create their ground profile, and they've then placed this onto the internet for anybody to use. And I guess the future developers will use this in their price modeling. So it's been a very powerful use of data, I guess. So yes, thanks for your attention. Should acknowledge Rasmus Klinkvort and Guillaume Sauvan, who actually did this work. And Rasmus did ask me to give a small plug for a Spotify podcast that he's chairing, and you can find that at NGI Technical. It is actually quite interesting, believe it or not. Thanks.
Thank you for sharing this. Is there any? Yes, Gregor, please.
Very interesting and outstanding presentation. And I would like to ask if the model was almost the size of Amsterdam, and you use it for later on, like prognosis of conditions in points that are not in the real points of drillings. What is the resolution? Because I think that it's a voxel model, if I'm correct. And what is the resolution of the cell?
I'm not entirely sure off the top of my head. I can ask my colleagues about that. I believe I've read that the resolution is perhaps to 1 meter in terms of spatially, but you cannot quote me on that. I think I'll have to check that and get back to you.
Thank you.
Any additional comment? Yes, from the back.
Stephen, I just wondered whether, I appreciate this is obviously site specific for what's being developed and put on the internet, but there's also potentially...
We can't hear you, Jonathan.
Yeah, we don't hear you very well.
Hello, can you hear me okay now?
Not yet.
Hello, is that better? Yeah?
Yes.
Okay. Yeah, Stephen, thanks for that presentation. Obviously, the data presented is for the specific site, which has been placed obviously in the public domain. One sort of possible loop of data which is maybe missing, which could then ultimately enhance the models moving forward, would be, you showed pictures of obviously maybe instrumented monopiles in terms of performance. We're obviously looking at potentially verifying things like PY behavior against the original design curves. Are you aware of any work which is being done in terms of trying to then connect the actual observed field performance against what you've actually correlated then as a predictive framework on the database?
I'm not aware of any public work that is available publicly on this aspect. I guess the Dutch government commissioned the whole ground model development to be publicly available, but then once it comes on to design of foundation and installation of foundation and management of those foundations, it becomes very much a, I don't know, I'd say, private matter of saving as much money as possible and not sharing your answers. I hope that changes with time, because we do have good databases of knowledge which everyone can use. Then if you don't actually have the database of the foundations placed on them, then it doesn't really, like you say, can't really be used going forward much in sort of back analysis studies. So perhaps we can get on to more contractors to share data.
Okay, we'll see.
Hey.
Okay.
Can I, one more small question?
Yes, go ahead.
I would just like to ask, how many people worked for how long on this?
I think quite a lot of people, maybe in the order of half a dozen, for perhaps 12 months. I was not one of them. So if there are any things I've said wrong, then I'm only the messenger. But you can find a full webinar series on the website I've mentioned, which has very detailed presentations on this, which are interesting as well.
Very good. So I think we are at the end and we should close our workshop. So thank you again. I would like to, let's say, thank you to all the speakers, particularly because keeping time was very easy because everybody made a perfect job and provided a nice contribution. Look, I'm clearly not an expert in this topic. For me, it was a personal basis, a very good opportunity to get an information on the state of the art, on what is going on in the research on this topic. So I think these workshops are really great. I was checking the people online. We were around a little bit more than 20 in the peak period. So considering that some of us are there, let's say here we are more than 30. So it's around 50 people participated to this workshop. And again, this is, I think it's a good record. It's a good data. And this morning, someone said, I don't know, maybe it was Fernando Pardo, not really sure, said we should open the workshops even further, not only to LGIP members, but well, this is already probably doing something in that direction. But here we have the GeoLab project. Maybe next time on mountains, we may try to push on that direction also. I don't know. We can try to, if we agree, we can try to open it to the general public, let's say. And with this hybrid approach, this is also an advantage. We can. And also, I remember the comment by Mauro this morning about promoting visibility. And I think that workshops could also be a good mean for promoting visibility of LGIP, because it's a way to share what we are doing and to the open public. Okay, so Peter, is there anything else you would like to add? No? So thank you again, everybody, also the ones online.
And the host, the excellent preparation of this meeting.
And of course the host, but the host will have to work 2 more days, so it's 3 more days, sorry, so it's not the end, it's just started, so you're getting trained. Today you got trained. Very good work. Thank you to the host. Bye bye everyone online also.